Hi everyone and welcome to CRISP-ML. This is the second video in the series where we are trying to understand gradient calculation and the role of learning rate. And here in this video we will be using a single neuron and understand its functioning and how its weights are updated. In the previous video we saw how gradients are calculated. We took up a simple equation y equal to a square plus b square to estimate a and b. We would now be focusing on working of a single neuron where we will try to see the PyTorch implementation and we'll try to match it with an example using the simulation in a spreadsheet. And for that example, we'll take the log function and we'll try to see the values of how weight and biases are updated. So let's look at the working of a neuron. Now this is a single neuron and as you would all be knowing, let's say there are n inputs x1 to xn and we have weights for each of the connections that is w1 to wn for each of the inputs, and we have a bias. And the way neuron functions is first it calculates the sum product of the inputs with all the weights, and then a single bias term is added, one bias per neuron. So here we have only one neuron, so we have one bias, and that is fed into an activation function. What does activation function do? We all know there are activation functions like ReLU, which filter out or which process the input coming from the neuron and then pass on the output as a final output of the neuron. Activation function is what brings out the non-linearity. So we have seen the functioning of a neuron. Now let's move on to applying it for our purpose. Right, we'll take a simple case. Here our y actual will be the natural logarithm of the input, and we will feed the input values for like 1 to 20, and the y value will be the logarithm of those values. Now here in our case there is a single neuron. We have x, that is a single input, we'll call it x. There will be a single connection, hence a single weight w. There will be a single bias, and our output will be nothing but simply wx plus b. Our goal is now to estimate w and b for the set of values that we are trying to learn from, that is the log function. We will have to choose a loss function, mean absolute error. Now here of course there will be no mean, because we have what we will do is we will feed the neuron one single data point at a time. For every iteration we will feed one data point which will update the weight and the bias. Okay, usually in practical implementations there are batches of the input fed because the data is huge, but here right now we'll just feed a single value. So if you have not seen the earlier video, I would highly recommend you check that out, because there we have seen how introducing the learning rate helped the solution converge to a proper value. So here it will be just the way we will update weights and bias is we'll take the partial derivative of the loss function with respect to the weight, and we will multiply it by the learning rate, and then we'll subtract it. This is by the definition of how we update the weights in gradient descent. Similarly for the bias term we proceed. Now here we have y is equal to wx plus b. We have the loss function as the absolute value of y actual minus y, and then of course what our goal is to find the derivative of the loss function with respect to x. So we will use the chain rule where the partial derivative of the loss function with respect to w will nothing be but partial derivative of the loss function with respect to y multiplied by the partial derivative of y with respect to w. And similarly for the partial derivative with respect to b, we have already seen in the previous video that the partial derivative of the loss function with respect to y is +1 where y is greater than y actual, and -1 where y is less than y actual. So here if you see y is equal to wx plus b, so the partial derivative of y with respect to w will nothing be but x, as this term b will be treated as constant, so its derivative will be 0, and for the derivative of wx with respect to w it will just be the coefficient x, And similarly, partial derivative of y with respect to b will nothing be but this wx term will be treated as constant, so the derivative of this term will be 0, and the derivative of this term b will be just 1. Okay, so putting it all together, so we see that the partial derivative of the loss function with respect to w is composed of two parts. The first part is the partial derivative of the loss function with respect to y, which is plus or minus 1 depending on the value of y, and the second part is x. Similarly, for partial derivative of the loss function with respect to b is again composed of the two parts, where the first part is the same and the second part is essentially 1. Alright, so I have this code in Python written. So for a single neuron, we will import certain libraries which are required, and then what we will do is we'll prepare the input, which I've taken as 1 to 20 as numbers in the float format as x, and y will be nothing but the log of those values. So we will just initialize and print them. So here we see these are the input values and these are the corresponding log values for the same. Okay. Now we will just initialize this random seed to 10 so that we get consistent values. Now we will initialize our model to a single neuron, which we will take help of the torch.nn library. So from PyTorch we have torch.nn, and we will take nn.linear as just one input and one output, that is the single neuron that we saw. This is what we will take here, and we will initialize its weights and biases. This we are doing so that we get consistent results all the time. Even if you run it on your own, you will also get the same results, and we'll just initialize and print them. Okay, now let's see doing this in the spreadsheet as well. Okay, so first epoch, our value for x is 1. The value for w, we have initialized it to 0.1455, which is also the value we have initialized here. And the value for bias is minus 0.739. These are just two values which I have found over iterations to be a good starting point. You can take any other values and you can try it out, and then you can post in the comment section below whether those values help your algorithm converge faster, give you better accuracy results, and so on. Okay, so y is equal to nothing but w times x plus the bias. Y actual here is the natural logarithm of x, and the loss function or the cost function or the error function is nothing but the absolute value of y actual minus y. The partial derivative of the loss function with respect to y will be if y is less than y actual, it will be minus 1, otherwise it will be 1, and this will be this multiplied by the value of x. And similarly, for the partial derivative of the loss function with respect to b will be this multiplied by 1. Okay, so we have all these in place. Then in the next step, so we will take, so the way we are doing it is we will be feeding the x values one by one in the sequence. Of course, this is not the standard way it is usually done, but for our understanding and ease of discussion here. What we will be doing is we will be feeding first x equal to 1, then x equal to 2, then x equal to 3, and so on and so forth till x equal to 20. And we will see how the values get updated in the background, and we will print all those values here and match them. Okay. So of course the epoch is 1. Okay. Now here we will update the weights as the previous weights minus the gradient, and of course, yes, we forgot the learning rate. So we will initialize the learning rate here to 0.01, let's say, and then we will take the previous weight minus the gradient multiplied by the learning rate. Okay, similarly for B, minus the gradient multiplied by the learning rate. Okay, and then Y, of course, all these are formulas, we can just track them. Of course, the learning rate we will have to copy it below, and all now everything has become formula, so we will just drag it. And D, we will just be careful not to replace it. Okay, and we will then also sum the loss values just to match it with our implementation. So we just say sum of these values, and of course we want to take a mean. Okay, so these are the values we get. So what do we see? We see, if you look at the error function, we see that we see a strange thing actually. So what we actually see here is that the error function is just oscillating, and there's no convergence per se, and the neuron is not learning anything per se. Okay, so this is definitely not a good choice of maybe the selection parameters or the methodology, or any of these steps followed here. Okay, we will for all we have done, we'll also see how it performs on some unseen data. We'll see in the program as well. So what we'll do is we will just extend this by one value. That is, we will try to predict on 21. For 21, what do we get as the loss or the error? Okay, so that is what this, we will treat it as a test value for us. Okay. All right. So now let's look at it from the code perspective. All right. From the code perspective, we have already seen till here. We have initialized the model with one neuron, one incoming parameter, that is the input, and one outcome. All right. So we will just execute it till here. And we have already initialized this model, since it is just one neuron with one weight value and one bias value. This is exactly the same which we have taken in the spreadsheet implementation, which is this and this 0.1455 and minus 0.739. And now what we will do is so for mean absolute error, of course, torch.nn.l1 loss is what implements the mean absolute error. And for here, usually we use an optimizer function to update the weights. Here we are using SGD because it simply implements the stochastic gradient descents formula, which we have seen earlier, which is nothing but weight minus the partial derivative of the loss function with respect to that parameter times the learning rate. So that is the definition which is automatically captured here, and we'll try to match it whether it rings out to be true. So if we take SGD here and we have taken the learning rate as 0.01, our results should be the same. Okay, let's check that out. We run this Now in number of epochs, so of course our number of epochs is 1. So we'll just run it for 1 epoch. What we do here is we, in the initial step, we make the epoch loss to 0, then we print the model weight and the model bias. And then we of course do the prediction as Wx plus B, and then which in the background would do it as Wx plus B, and then the loss function is nothing but the criterion, and the criterion here is the L1 loss. Okay, so that is what we are using, and that is the loss we'll calculate. We'll add it to the epoch loss, and then we will print the loss value for every epoch. Okay, for every iteration, sorry. And then before we update the gradients, we will just make it 0 gradient. Okay, and then we'll do the backward pass. Okay, this is a step which will automatically calculate the gradients for weight and bias. Okay, and if you remember then we'll of course print the weight gradient and the bias gradient. And if you remember in the previous example in the last video, we had detached the parameters A and B from the graph, and we had updated it by writing the formula here, that is weight A minus the gradient for A multiplied by the learning rate. But here we'll let the optimizer do it, and it should do the same thing, and that is what we will see. So this is a standard methodology, a very high level basic methodology of a neural network loop in PyTorch, and this is what we are trying to match it with the Excel implementation. So let's execute this, and of course in the end we will be printing the epoch value, we will print the epoch loss. Okay, so let's run this. Alright, so if you see this we have run. Okay, now as a quick check, if you see the epoch loss is 19.40410, which if you see here, it is exactly matching with what we have calculated here in the Excel. So we are almost accurately to the point here, and then of course we match the gradient values as well for a few epochs. For the first epoch, of course, the values are same which we started with for W and B, and the loss is 0.5935, which is the same, but obvious. For the next epoch, the value of W is 0.1555, which is the same which we are getting, and then the value for B is minus 0.7290, which is again the same that we are getting. So similarly, now we'll just check the last iteration, and then that is here we have the tensor value, which is here. We have 0.2455 for the weight and minus 6.89 for the bias for data point 20, and the loss is 1.22526. Although this is not a very good generalization, but at least we have now seen how this gets updated in the background. So how torch.nn.l1 loss functions, how the optimizer, which is the SGD, that functions. We have taken a very simple case, as I will repeat here. We are feeding one data point at a time in like the batch of one and in sequence. This is not the way in standard implementations it is done, and we will see in future videos how randomization or using batches and or mini batches helps in the practical computations. Let's check what the prediction goes for the value of 21. So what we will do is we will see it for 21, how much is the loss we are getting. Okay, so we have to give it as 21.0 because it's expecting a float value. Okay, so if you see this here, we have seen the loss value of 2.788, and if you see it here, it's exactly matching with our implementation. Okay, so this is not very encouraging. So what might we do to improve this? So will decreasing the learning rate help? Well, let's see. If we make it 0.01001 instead of 0.01, will it help? Well, it does look like something does seem to improve. If you see here, our loss function. Initially it rises, but then it drastically comes down, and then it starts oscillating between two values, almost two values. Okay. Also, the value for the predicting the value for 21, the loss is now much lesser, as we have predicted 3.1245. The actual value is 3.0445. So we have come very close, but then let's not be too enthusiastic with this, because we know, right, that our last computation was on X value of 20. So it is very close here. So we have only one neuron, one weight and one bias. So since it is close to 20, it will always be likely to be accurate. But still, it is an improvement over the learning rate of 0.001. Since 0.001 is better than 0.01. So let's see if we do it. More values. What happens? Okay. Now the error slightly increases. And it also converges a little slower, but I think if we drag this down, we will have a much more peaceful conversion, and then maybe, as we saw in the earlier video itself, there will be some oscillation when it reaches the endpoint value. So this is a pretty decent performance, I would say, for a single neuron, just learning from 20 values and trying to predict on one value. By the way, if you noticed, for 0.001, the overall epoch loss has also gone down from 19 to 16.46. And if we make it 0.00001, so epoch loss increases, but I think it will take more steps to converge. Alright, so we have seen for these values we are getting so much as total epoch loss and average epoch loss per data point. So let's say 0.823 is the value. Now let's say we run it for one more epoch. So let's see how it simulates. So what we'll do is we'll just completely copy this and run it in the same way again. So again, I would reiterate that why we are choosing to feed it in a sequential fashion is so that it's easy to implement in the same in Excel and show it in our discussion. Okay, so of course this is a fixed value. We'll have to update it with a formula. So this will be the continue. So what we have done here is, this is from the epoch values to, we have refed the data again. And if you see here, again 1 to 20 values are fed. The formulas are the same. We have just dragged it down and we have updated the weights and biases. Now let's check what is the epoch loss for the second epoch. So let's copy this here and then paste this here. So this is nothing but, if you see here, from the second epoch, it is adding up all of them and this is averaging out. So this is reducing. So if you see how multiple epochs leads to a reduction in the loss function value. If you just plot a graph for these value, you will definitely see a fall. Alright, thanks for watching. In the next video, we will see the single neuron gradient calculation using the mean squared loss function, and we will continue our discussion there. Thank you.